In this problem, we're given a function and we're asked to analyze the geometry. We'll state the intervals of increase and decrease, relative extrema, asymptotes, intervals of concavity, and any inflection points that occur. So let's proceed with the asymptotes first. There's horizontal asymptotes and vertical asymptotes to consider. And to find a horizontal asymptote, you need to determine the value of this statement here. Where's the function going as the input x gets infinitely large, as it approaches infinity? So if you can just imagine this function here, 6 divided by x plus 7. The bigger x gets, the larger the denominator is going to be. So if we were to divide 6 by a larger and larger and larger value, ultimately it's just going to get closer and closer to 0. So the horizontal asymptote just corresponds to that y value. The larger x gets, the closer the y value gets to 0. So a horizontal asymptote is the horizontal line y equals 0. The vertical asymptote is going to be the input such that the function is either approaching positive or negative infinity. So is there a value of x such that as x gets closer to that value, we'll just call it a, the function either gets infinitely large or infinitely small. And the easiest way to think about this is, well, we've got a denominator, and if we divide a value by something that gets closer and closer to 0, then the associated quotient is just going to get either infinitely positive or infinitely negative. So the easiest approach to finding a vertical asymptote is to just look for values of x that make the denominator 0. In this case, if x is negative 7, we've got a 6 divided by 0 situation, which corresponds to a vertical asymptote. So here's the two equations associated with the horizontal and vertical asymptote. All right, so and I'll label this asymptotes. So next up, we're going to look for the critical values because we have to find the intervals of increase and decrease and then any relative extrema. So to find the critical values, we need the derivative, which we'll set equal to 0, and we'll determine if there's anywhere it doesn't exist. So we've got a quotient here. We could use the quotient rule. However, we could also use the chain rule. If you look at this, the numerator is just a constant term. There's no variables in it. It's just 6. So it would be useful to just rewrite this function with that x plus 7 to the negative 1 in the numerator's place. We'll bring the x plus 7 up, raise to the negative 1. That way we can use the chain rule. It just makes it a little more straightforward to find the derivative. We'll bring the negative 1 down, multiply the 6. We'll rewrite the x plus 7, reducing the power by 1. So now it's to the negative 2. And then multiplying by the derivative of x plus 7 is just a 1. So this is the derivative here. Might be useful to rewrite it with positive exponents so that it's very apparent that that x plus 7 is in the denominator's place, or x plus 7 squared. And there's our derivative. So to get the critical values, we need to set this to 0, right? We need to figure out where does the derivative equal 0, and or where does the derivative not exist. Now in the case of a fraction, like we have here, fraction's only going to equal 0 if the numerator is 0. And the bottom is not also 0 at the same place. But in this case, the top can never be 0. It's just simply negative 6. Negative 6 never going to equal 0. So we have no values of x that are going to make our derivative equal 0. So no critical values here. Now for fractions, if you're interested in places where they do not exist, then we want to look at the denominator. If the denominator is 0, we'll have a value that is indeterminate. The derivative won't exist anywhere that x plus 7 squared equals 0. So setting the denominator equal to 0, we should get x equals negative 7. and this is one of the reasons why I chose to do the asymptotes first. When you have a vertical asymptote, that should always show up as a critical value. It's not, this -7 doesn't correspond to an ordered pair. I mean, if you were to plug -7 into the function, you're not going to get a value out of it, right? Because it's not a coordinate point. It is just an asymptote. But it's very apparent now that, that x equals -7 we weren't surprised to see that as a critical value because it is a vertical asymptote and a function can go from increasing to decreasing over a vertical asymptote. So we have no ordered pairs associated with our critical value, so we won't have any extrema. There will be no relative extrema for this function. But that -7 should still go on our number line to determine our intervals of concavity. So great way to get this done, right? If you consider the first derivative test, if the first derivative is positive, the function must be increasing. If the first derivative is negative, the function must be decreasing. Well, if you look at our first derivative, it's always a negative value, right? The bottom is something squared. So assuming we're not at -7, the bottom's always going to be a positive value. We're squaring it. The top is always -6. So no matter what value of x that we choose, to the left of -7 or to the right of -7, we have a negative first derivative, which means the function's decreasing on both sides. So as far as our intervals of increase and decrease is concerned, this function is always decreasing, except for at -7. So we'll say the function is decreasing from -infinity up to 7, and then from 7, or sorry, -7, and then from -7 onwards. At -7 itself, we've got a vertical asymptote. So it's likely the function looks something like this, perhaps, right? Always decreasing, but over -7, the function doesn't exist. So we've got our interval of decrease, and then as far as our intervals of increasing is concerned, we would just say it's never increasing. We had said there is no relative extrema because the only candidate for a relative extrema would be the critical value, and that critical value does not correspond to an ordered pair. Right? So there is no place on the function where we reach a relative max or min. Okay, so we've got the intervals of increase decrease. We've stated that there is no relative extrema. We've stated the asymptotes. Now we'll go for the intervals of concavity, for which we'll need the second derivative. So the second derivative, we can use the chain rule again. No need to use the quotient rule. We can just use this form of the second derivative. Right, we'll bring the -2 down, multiply the -6, gives us a +12. We'll again reduce that power by 1 on the x plus 7. And then multiplying by the derivative of x plus 7, we still have this 12 times the quantity x plus 7 to the -3, which maybe it's better to rewrite with the positive exponents again. Now, if you have a vertical asymptote, that vertical asymptote will show up on both number lines. I've got it here when we looked at the intervals of increase, decrease. It's also going to show up on our second number line when we look for the intervals of concavity. Every time, if you have a vertical asymptote, that x value will show up on both number lines. The definition for finding inflection points, which is really what we want here, is where does the second derivative equal 0? But if you look at the second derivative, again, it's a fraction. The numerator can never equal 0. So we don't have any values of x where the second derivative equals 0. We've got no inflection points. However, there is that value x equals -7 where the second derivative doesn't exist. And we can't call this an inflection point because it's not a point. We had already established that at x equals -7, the function doesn't exist. So we're not going to call it an inflection point. It is, however, a value of x that we want when we look to state the intervals of concavity, because at a vertical asymptote, just for example here, right, a function can change its concavity. We can have a function that's concave down on one side of a vertical asymptote, concave up on the other side. So we have no inflection points, but we do have that value x equals -7 to consider when we define the intervals of concavity. So no inflection points. But let's fill out the left and right side of this number line here to finish off the problem. So if we look at our second derivative, right, the idea behind concavity here is that if the second derivative is positive, we will have a concave up function. If the second derivative is negative, we'll have a concave down. Now in this case, the numerator is always 12. It's always a positive number, so we can really just look at the bottom. And in this case, we've got the denominator being cubed, so you can get a signed value out of something being cubed. If x is smaller than -7, so you could choose really anything. We could choose -10, -9, whatever. But if x is smaller than -7, we're going to get a negative value out of the denominator. 12 divided by positive 12 divided by a negative number is a negative number. So to the left of -7, we are going to have a concave down situation. Right? The second derivative is negative if x is smaller than -7. If we choose a value larger than -7, let's say x equals 0, we're going to get 7 cubed in the bottom, which is a positive number. Positive 12 divided by a positive number is positive. So we'll have concave up to the right of -7. So we'll state the concavity here. Just interpret that number line we filled out. But this will be concave, let's see, concave down and concave up on those associated intervals. So we've got concave down from -infinity to -7, -infinity to -7, and then we're concave up from -7 to positive infinity. And that should be the entirety of the problem. Now what you could do here, you really could do this from the beginning as well. We could plug in the original function into the calculator just to check our work. X plus 7, oops, I got that in the wrong spot, 6 divided by x plus 7. We can look at a standard window. So we're expecting to see a vertical asymptote at x equals -7. Here's x equals -7. That checks out. We're expecting a horizontal asymptote in y equals 0. So if we were to visualize this horizontal line y equals 0, it looks like the function does approach that line. So the horizontal asymptote checks out. We are looking to see the function decreasing to the left of this x equals -7, which looks like it does. We could even zoom out if we wanted. Function's definitely decreasing to the left of -7. It's also decreasing to the right of -7. There is no relative extrema, right? The function's either it's always decreasing. There's no place where it tops out or bottoms out. There's no inflection points. And the concavity seems to match as well, right? To the left of -7, we've got this concave down shape, and to the right of -7, we have this concave up shape. So that should be the problem. Hopefully you find that helpful. Thanks. Bye.